Let's calculate the Laplace transform of some very important functions, beginning with the exponential function. The exponential function is defined as 0 for t less than 0, meaning for the negative time values, and a times e to the minus pt for positive time values. That means that in 0 the function takes the value a right here, and as long as p is positive, the function decreases and approaches exponentially 0. It converges to the value 0. The bigger p is, the faster this function approaches 0. This effect will be very important in the future. So let's calculate its Laplace transform by applying directly the definition of the Laplace transform. F of s is equal to the Laplace transform of f of t, and this is the definite integral between 0 and infinity of f of t. Since we're starting in 0, we only care about this part. So this is a times e to the minus pt times e to the minus st dt. And now we have to remember our knowledge on integrals, on integral solution, integral calculus. We have first of all to take a out of the integral. Here it is, a times the integral from 0 to infinity, and we can write this product as e to the minus p plus s, all that multiplied by t, here dt. Now we have to remember that the derivative of a function e to the z x, the derivative of this with respect to x is e to the cx times z. So if we can get this inside the integral, we already have the solution, its solution. So the trick we use here is to multiply and divide everything by p plus s, by minus p plus s. So outside of the integral we have minus p plus s times the integral from 0 to infinity of minus p plus s times e to the minus p plus s t, all that times dt. And we already have a solvable integral. So the solution is a over minus p plus s times e to the minus p plus s t evaluated in 0 and infinity. So we use these two values here on this t, and we get again a to the a over minus p plus s, here a to the minus p plus s times t is times infinity, which means that here we have e to the minus infinity minus e to minus p plus s times 0 is 0. So here we have 0 and here we have 1. So this minus 1 goes with this minus sign here, and the final result is a over s plus p. This is the Laplace transform of the exponential function. The next function whose Laplace transform we want to calculate is the step function, defined as 0 for negative time and a constant a for positive time. That is to say, the function comes here, and in t equal to 0 it goes up until the value a and keeps this value from then on. This is the time scale. In the case of a being equal to 1, we call the function the unit step, or the Heaviside function h of t, and we'll use this unit step, this Heaviside function, a lot during the course. So again, the Laplace transform of f of t, that is to say capital F of s, is Laplace transform of f of t is equal to the integral from 0 to infinity of f of t, which is a times e to the minus st dt, and we'll use the same tricks as in the previous case. A multiplied by the integral from 0 to infinity of e to the minus st dt. We need to multiply and divide everything by minus s. That's what we do. And here we have minus s, and here minus s, so that we have a direct integral here. All that equals a over minus s times e to the minus st evaluated between 0 and infinity. That is equal to a over minus s times e to the minus infinity minus e to the 0, which is equal to, since this is 0 and this is 1, this minus 1 cancels off with this minus, and finally we get a over s, which is the Laplace transform of the step function, and therefore the Laplace transform of the unit step function has to be 1 over s.